have all the walls there, wall size. Actually, you guys actually already size up. So now assume that all lateral deflection is all okay, met, and so that all column and wall size and beam size completed. Now time to move on to the foundation system. So what I'm showing here is just in case, because always the model, when I worked on, I cross check whether current model is real, whether this is perform to the level I'm expect. So here is actual force diagram under the gravity load. So now I'm gonna show you how to start adding the foundation system. So here I'm gonna just go all the way down at the basement level, right? Control D. Okay, here is a grid. Control D. So those are all my wall joint and also column joint here. So one thing is same things. So in order to add elements, you need to set the material property and section properties. Let's say slab. I'm gonna add mat 7 feet. Oops. 7. Let's say 7 feet mat. Concrete strength here, I will assume 5,000. So this is 7 feet. So 84 inches. Here, topic, property type, mat. I'm gonna choose. I'm gonna use just thin shell thin. We can use a thick as well because it is relatively thick. So obviously this is section properties, right? So there is just mat, and you could draw the now mat by picking up the column. Oh, okay. Let me redraw it. Okay, I'm choosing it here. I'm gonna choosing 7 feet mat here, and click and click there. So I add the mats. Now one thing, if because I just click the nodes, column node joint, obviously physically the column cannot sit on the edge of the mat, right? So I have to physically extend this. So ETABS has good feature. I can expand, edit shell, expand, maybe 5 feet, so 60 inches. So I expand this, right? So this is my mat, 7 feet mat. I'm just draw the graphic here. So mat here, and if you want to turn on this here, see the extrusion. So I add a mat foundation. All right, now we just, after we draw the mat, I'm gonna select all the nodes and get rid of a joint boundary condition. So I select all the nodes, 0 boundary condition. Instead, I'm gonna pick up this mat and assign the area boundary condition, which is a soil spring. So this soil spring, we need to define, where is that soil? Oh, here, spring area. Here is area spring, right? Area spring. I'm gonna create, this is, let's say 10 ton soil. Oh, this is inches. I need to change to feet. Let me just change feet. You put, I'm gonna again open the area spring and open this. So here is vertical direction. We're gonna assign that based upon soil spring here. Yeah, so here. So we're gonna use a soil spring modulus subgrade modulus 480 keep per cubic foot for 80 here. So we are assigning vertical spring. Now, typically soil is only work for the compression, so we need to choose the compression only. But one thing that we need to think of later, assume current all the mat is experiencing the compressive stress, which means no uplifts happening throughout our building. So it could just, for now, keep it as a compressive only. This spring is only working for the compressive stress. All right, so I assign this spring constant. Again, select mat and assign shell area spring. I'm going to assign area spring to the mat. So let me show you. So basically, now all the boundary condition gone. Instead, this mat, when you select it, you have a soil spring. This is boundary condition for this mat. So it's almost ready. But one thing that I'm gonna edit more, because I only apply the vertical springs, which means this building doesn't have any resistance on laterally. So I'm gonna just pick up the points and assign only spring restraint X and Y, not vertical, so that this building doesn't move under the wind load, right? So this basically, before we have a pin XY vertical restraint, but since we apply only vertical spring when we define the soil spring, this as it is doesn't have any XY restraint, so that I'm currently select all the corner nodes and assign the restraint X and Y direction. All right, so basically it's ready. So 7 feet mat is supporting 40-story building model. I'm gonna run that and see. I'm gonna show you the soil bearing stress under the mat. Okay. So I'm gonna show you the soil bearing stress based upon that, and SDL library is total gravity effect, and show you. So this is soil bearing stress. It's simple. Basically, this is overall that plus SDL and LIBOR divided by this area of the mat. If you think of the spread frame design, you do this first. Total dead and LIBOR, right? Divide by your bearing, allowed bearing capacity, which you are calculating required area of the footing, right? If you choose the your footing side, assume that we already did it. You draw, size it. So total that SDL library divided by this mat area, which you can roughly calculate the soil bearing stress. But what you did was this based upon, because a small scale, you assume that uniform distribution. So basically, you don't differentiate the stress gradation. Basically, total depth plus library divided area. So you say all the loading is uniformly pressed down. That is your footing design philosophy. But the building scale, soil is not going to be uniform. This building and your loading, right? We have a various loading intensity from the column, wall, so that your soil stress underneath the mat is not going to be uniform, right? What you see is based upon your total loading from the wall in each column, it shows the soil bearing stress underneath. So this is actually contour. You see this. Basically, what you see this in the morning, check your mattress. That shape, if you see, you may see something similar, right? So overall loading pressing down your mattress, but you have a different load and application point, right? Obviously, under my maybe body, right? Their intensity of loading is different, so then you're gonna end up with various sort of bearing. So typically, this is first trial. I say that okay, based upon this, I'm looking at maximum soil stress, bearing stress of 14 and 4, which is biggest soil bearing stress occurring in the middle. There's more intensity loading is coming from the tower. So 14 KSF, which is 20 KSF is our limit requirement. So which is okay, right? Now, this is only gravity effect. How about the lateral effect? Let's say lateral effect. So we're gonna create another row combination engaging the wind and together. So current AS is 7. We typically using WinX. Maybe do I have yeah, let's say. So I'm gonna add win. Okay, win 0.75. Since the live reduction time 0.75. So this is load combinations is for the gravity and lateral effect, combined effect, load combination I'm setting up. So live load already have 0.5 reductions and multiply by 0.75, so that I end up 0.375. For wind effect, oh, hold a second. I need to, if this is ultimate loading, let me just change to SD. So basically here, I need to use 0.6. Because this wind is ultimate. Because this wind, I set it up ultimate, I'm sure you guys actually ultimate wind load, right? But since we are using AST method, allowable load stress method, AST method, this is a load combination from AST, total dead load 100%, with a live load reduction and wind ultimate load. So this one wind should be scaled down to the AST or the service load, so that your load combination should for the live load is 0.5 times 0.75. For the wind cases, you need to use a 0.6 factor times 0.75. So this is your final load scale factor. Here, let's try it. So we're gonna use it. So let's change to low soil bearing for, yeah, this. So what you see, gonna stress maximum bearing stress shifting, right? You could see the gravity and wind X effect, right? Let me just show you one more again. If you take a look at only gravity, it's more concentric, right? But when we turn on this gravity effect and lateral wind, the first wind here, mode 1 or step number 1, is the wind is blowing in X direction. So you see that because overturning effect, the opposite side, rear side of this wind, gonna cumulative gravity effect and the lateral effect. You see the maximum, the compressive stress is occurring on the right side. If you use second one, you can see that again, gravity effect, but wind is pushing up, so it's overturning effect. This tension side, opposite side of the wall is compression side. So you see that this is shifting to up, right? This is based upon just the load effect and other maybe 3, 4, 5. You could take a look at it. They are pretty much similar. So this is first. I want you to just test it, set it up, and include this your foundation design, right? This is kind of first sizing check. Whether all the stress based upon AST method is under our design allowable bearing capacity. So choose the shell. Okay, go back to this. Since I already set up the load combinations, I'm going to click this shell here, shell stress. I'm going to take a look at the first gravity load combination. Okay, since we are talking about vertical shear, we need to look at the S13 and S23. It's a vertical the shear stress, which is default. This is local axis 1, local axis 2, outer plane is local axis 3. Okay, so I think you need to get familiar with the global axis and local axis from now on. If you're running any of these finite element software, so I will show you that the default. I will show you here. Maybe here check. Right. So red is local axis 1, green is 2, outer plane is a 3. So this is default setting, and we're gonna open this one of load combination. I will choose number del plus live load. Check the shear stress. I'm gonna check the shear stress on the plane in S13. 1-3 plane is basically when you cut the section like this, the shear stress is on this cross section. Those will be shown on the plan. So the ranges we take a look at 212. Oh, this is okay. Let me change to PSI unit since we are using unit PSI. Again, PSI. Okay, 1-3. I'm gonna type 212. 212 because this is concrete shear strength. So this is PSI. Again, this is the shear stress diagram. Shear stress diagram S13 when you cut the section, because this is at this outer plane in 3. So I'm cutting section here 1-3, right? On the plane, the shear stress is shown on the plane. So you see that relative to some significant force, the shear stress. You see that at the corner of your core wall, because this that is the most heaviest force intensity coming from. How about S2? Right, S2. When you cut the section on the plane S2 and 3, right? You see that just next to your core wall, gonna experience more shear stress, right? Okay. First of all, is observation. Observation. I want you to, because I think undergraduate you guys didn't take any FM courses. It's something graduate level. Finite element software is mostly graduate level courses, but I think you could understand in general, because this might be the first time you've been seeing this finite element software, but basically your spread footing design is identical with this. So we are just stretching into the element larger scale. So the soil we're going to experience, this is the shear stress we are currently look at it somehow. Current model 7 feet mat experiencing a little bit of shear stress. Oh, wait a minute. Yeah, I have to fix it. Oh, I have to use the ultimate load combination. Let's go back to this. Yeah, so this is the load combination. I choose 1.2 DAD, 1.6 LIGO. So this is ultimate load combination. I'm showing you S13. So you see that there are quite significant shear stresses formed next to the core wall in S13 plane and 23 plane, which means, let's check it, 283 psi is overall exceeded 300, which means my current 7 feet mat experiencing or exceeded the shear stress. So we need to think about then, okay? There are two choices, mat or beam. If you have excessive shear stress, what do? Increase the member. Or we have to add a shear reinforcement, right? It's identical. The approach is identical. It's only two way. So this mat is experience significant. So I think maybe let me just, all right, size up one more time. One time. Okay, 7 to, let's say, how about the 8 foot? So I'm gonna just use 8 foot. Or I can increase the concrete strength. Currently, so we have three choices, right? This is actually design and selection of the member sizes. When you design the beams, same thing. When you estimate all the design forces, you check the shear and the bending at the same time. In these cases, we are currently checking the shear stress is beyond our allowable shear concrete strength, so that significantly, so that I decide to increase the mat thickness. So I increase to 8 feet. So I'm gonna show again. So see, this actually went down a little bit, but so shear stress is the one is driving our member size, right? Now, one thing that because the scale is and also it's localized, the shear stress, excessive stress, shear stress. So I show you because our current system we have a large forces coming down from the core wall. So what is the strategy? Thickening up the locations, right? Instead of increasing entire thickness, right? That's why, yeah.
And then that max min like value, like
Yeah.
range of 212
Yeah.
pounds per inches squared.
Yeah.
Is that going to be generalized for all of our designs? Is that
Yeah.
the code? That's the maximum.
Yeah.
Okay.
Because I currently choose a 5 KSI PSI concrete for the mat. Right.
If we were to increase.
If you is a designer, typically so far, I think 5,000 PSI concrete is a pretty common for foundation design. I think since high strength concrete is available, premium is not that much. I think since 5 and 6 is pretty common, not high rise. But typically low rise, you just use 5 PSI. But high rise building for the mats, I think 6,000 also, I believe, using it. So, but obviously this is just based on formula, two-way shear, right? Concrete. So why the shear? Because I think in your concrete beam design, you already learned it. The shear force is going to develop diagonal tangent, right? So we usually add the shear strop in the beam, right? But somehow here, question mark is, oh, this is mad, it's two-way. What is kind of shear reinforcement arrangement do we have to apply, right? So first thing is we need to this scale, we iterate it, find kind of reasonable mat thickness. It's gonna be a one big thick mat or separated, depends on their demand. These cases we have large concrete over here. Makes sense. We can thicken up only locally here, right? Outside can be thinner. So I think the current model I didn't differentiate it. So if you can divide this. Maybe we'll try. Let's try. Because let me show you. Let me draw. I need bind. All right, so what I'm gonna do just for example, so I'm gonna draw another mat. This one assumes 8 feet. The other one I will assign is 7 feet. All right, those are non-members, so it doesn't matter. Non. So this case is gonna save ETABS. They understand that if you end up with the two overlapping elements, there the smallest one is superseded. So basically, if I model like this, only this area is 8 feet, outside is 7 feet. All right. So let me just run it, and I will show you and move on to next step. So assume that we size the mat for the shear. So assume that shear stress, maximum shear stress is less than our allowable shear strength. And now we're gonna move on to mat foundation design. I'll show you the shear stress again. And this is shear stress based upon 1.2 dead, 1.6 live. If you want to see the wind effect, you need to also check the shear stress as well. All right. Okay, now we're gonna move on to the member design. The one things I'm gonna show you two methods. There is a FM method and the stream method design. What we can do, we're gonna draw. Now I'm gonna use a fit. The design strip. So here there is a design strip. No. Where did it go? Okay, right. So design strip for speed up 10 feet, 15 feet, 30 feet, 30 feet, maybe 30 feet. No, so 15, 15, 15. Yeah. For speed up, I'm gonna make the design strip like that. Hold on, let me turn on this design strip here. Where'd it go? It doesn't show the design strip. Hold on. Okay, show is okay. Design strip here. Strip layer A, column strip A. Okay. Oh, okay. All right. So design strip. I'm gonna draw. I have to choose so far away. Okay, design strip. All right. All right. So design strip, I'm gonna draw. I will show you. Hold up. Let me just. Did I overlap it? Oh no. Again. Okay. Go to here. Design strip. I'll choose A direction is Y directions. All right. I'm gonna copy design strips. 35th spacing. 1, 2, 3, 4, 5. So I'm I just drew the design strip one directions. I'm gonna do the same thing on the layer B7, same thing. I'll just do copy Y direction as well. Wait a minute, color, is it same color? Let me double check. Okay, should be fine. And copy, replicate Y direction. All right. All right. So basically, this is design strip. Because of this finite element software, I need to collect the forces. So I draw the column strip in A and B, X and Y direction. I'm gonna run the model. So what I'm gonna show you is design forces in the map along their own X direction, Y direction map. Basically, this what I'm just trying to show you is basically identical with your beam design. But beam is mostly one direction, but med is two direction, X and Y. So when I cut either this, means all the forces spanning in this direction, and try to show you the design forces. If I cut this section, they are collecting the forces in Y direction. You show the design forces, which is a shear and moment, and actual force, right? So, all right. After this, I'm gonna run the reinforcement design, so I will show you. So at this point, and strip, okay, here, display. Obviously, all these forces is in the display, and right here. Hold on. The display strip forces. Okay, I'm gonna choose the 1.2 that 1.6 live road. Okay, first of all, moment diagram in X both direction. So let's see, first of all, one direction. So what you see is a moment diagram along this entire building matched in Y direction. So you see that by the moment diagram, and up and down, because it is a continuous, the mat. See, they collect the forces within this design strip, each design strip, which I assume 30 feet for simplicity. So you see that moment diagram along this cross section. And you could see the shear force diagram as well, right? So this is the design forces we are using for reinforcement flexural design, moment and shear. And we could take a look at in the Y direction, X direction as well. So this is most likely the design strip does the collecting the forces, and we can use this, the ETABS is use this design forces for flexural design. Now, the model is ready. I'm going to show you and design. We're going to run the concrete slab design here. Concrete slab design here. And I'm going to choose the story base. Right? Okay, design, slab design. Here, let's see what kind of load combination. Oh, we need to define load combination. So this is load combination. We set it up. We need to cross check, but you see this. This is 1.6 and 1.6 live load. This is 1.2 live load and win loading. So this is all load combination. We're gonna use it, and we're gonna run the design. So I'm designing the flexural rebars. All right. So just design procedures done, and more common practice how to see the design force, flexural bars is right there in concrete slab design and display flexural. And we're gonna use for a strip basis, which since we defined the design strip, I'm gonna include the minimum, right? And instead of showing the boss, I'm gonna show the bottom rebar. I'm gonna choose minimum bar with the play with the bar. I select the bar number 10 inches, number 10 bar. For now, 1 foot spacing. And additional bar, if I need it, I'm gonna use the number 11 bar. So here, because the design is complete, this is also output module display how to turn on and off and check all the rebar and their necessary location here. So I want you to include this output as well. So this is a map foundation design procedure. I want you to follow along. I'm gonna upload this video too, but you need to just follow along. But overall, remind yourself is a spread frame design procedure, and this is almost identical. This is only tool finite element software, right? So that if you follow along, I think you may get there. So now, this is some additional. Now, during the design phases, this is output. We need to really iterate and see to find out what bar and spacing is do we need it. So change to inches and output again. So here, let's see. So reinforcement, we are looking at a bottom bar in Y direction. I threw out the bottom bar number 11, 12 inch on center. Still, we need additional bottom bar like this, which means it's pretty significant amount of bars. So I mean, reduce the spacing. Okay, so this is spacing. If I throw out number 11 at 6 inch on center, most of area is all okay except few outside, and you see they still under this core. We still need quite significant amount of additional bar here, right? And I think you could do the top bar, right? This is top bar if you're using 6 inches, right? This is additional bar. So this is mostly output. Graphically, you can figure out how much reinforcement do we need. So again, after analysis complete, save ETABS, analyze overall area of bars. Now what size of a bar and spacing of a bar and where is something graphically you could go walk through and you choose it. We are the engineer, we choose it. So we need some iteration to choose the number of bar and location of bar. So I want you to play with this and show the bar, choose the number 11 bar and spacing. Number 11, 6 inch on center is a pretty quite dense, congested, right? Because number 11 bar eventually have lapped on in the mat. So 6 inch on center is pretty quite congested. So you could just bundle it. So you could use a 2 bar, right? Side by side, the bundle, we can bundle it, and you can use 12 inch on center as well. But because the scale of mat is humongous, so we And most likely, just by looking at this, we need a multi-layers. It's not gonna be a one layer. It may be two, three layers at the bottom bar in X direction, Y direction. You could um, think of based upon intensity of rebar. Okay, so I'm gonna